This is going to be the 14th and the last presentation which I would be delivering under this 2 years PG program. So once again and for the last time, I would like to start with warm greetings to everyone. My name is Chinmay Vinay Dandavate. Currently I am in the 4th semester of the M.Sc Statistics program and I am pursuing this degree from the Institute of Science Nagpur, which is an autonomous college under the government of Maharashtra. The topic which I have been allotted to design a presentation for this course based on the computational statistics is the bandwidth selection and the cross validation, where the topic of cross validation further subsequently gets disseminated into its types as the least square cross validation and the maximum likelihood cross validation. So let me start with a very generic statement about the relation in between these two. So here I have a very generic statement to offer, or a very overt comment to give on the relationship between the bandwidth selection and the cross validation, where the latter forms a medium to the former. That is, cross validation forms a medium for the bandwidth selection, or it forms a ground of action for the bandwidth selection. Now, if you look at the very framework of this course based on the computational statistics, you will find that this topic, which I have been allotted to design a presentation, forms a good half unit. That is, it forms a good 12.5% of the entire course. But then, given the fact that we have successfully completed 3 semesters, that is, we have completed 75% of the course successfully, and now we are pretty much aware and familiar with the structure of the exams and the state of affairs which succeed and precede the exams. So my intention here won't be to present this topic from an exam oriented perspective, a strictly exam oriented perspective, rather would be from the perspective of the formation of a strong foundation to the enterprise of machine learning. So as I have done so far, or as per the philosophy which I have followed so far, I would like to introduce this topic by using an example, by connecting it with a real life situation. So here we have a case with us. Suppose a college has to know how the students will perform in class 12th for a given year, a given batch, so that they can make arrangements for the in terms of the number of classrooms, the number of teachers to be employed, the number of seats to be arranged, and so far. So the results of that particular year are yet to be declared, and they have got information of only 6 children's score by far on the basis of the responses which they have given. And now they have to estimate, or they have to make an estimate of the scores of all the students appearing in class 12th for the given year. But then how can that be done? Because the total number of students who have appeared for class 12th for a given year are pretty large in number. The magnitude of the students who have appeared for class 12th exams in that given year is pretty large, and we have only the scores of 6 students in our hand. So how can this estimate be made about the scores of all the students on the basis of these 6 students? A visceral part, a vital part of the presentation is going to be an answer to this question. Kernel density estimation can offer a great solution to this problem of making an estimate about the large population on the basis of a small sample which we have in our hand and which is known to us. And in fact, it can be very well put in a pictorial form where we can see that we have a small sample and we have to make an estimate, or we have to make some prediction about the large population, and this creates a bridge between the sample and population. And this is nothing but the sum and substance of the kernel density estimation. So the very first step, or the very first block which needs to be casted in this sample to population bridge, is to represent the sample which we have in our hand in the form of a number line. So here it can be seen there is this number line on which we have plotted all the 6 observations, and in fact we have went an extra mile. We have done this additional task of classifying or dividing these scores into 3 categories, where 45, 52 and 58, they are regarded as the struggling category, the category of scores which is pretty struggling, whereas 78 and 82 is regarded as an average category of scores, and 95 is considered as a high achiever. But then the immediate task which is at our hand, or which is to be carried out, is how this data which is in our hand can be transformed into a unique mathematical statement. In order to make estimate, or to make some substantial and solid prophecies about the entire population, the entire uh, class or mass of students who have appeared for the class 12th exam in that given year, we have to make some unique mathematical statement. And in order to go ahead on the same lines, we have to transform this number line to graph and form bell-shaped curves where the peak of each curve lies on the given point, thereby creating 6 bell curves. So here, as it can be seen, we have formed these 6 curves where the peak of each curve lies on the given point. And the major change which occurs while we make this transition from number line to this graph is that while we were in the realm of operation of number line, each point had a very limited information to give. That is, the point had only its own tail to tell. But here, while this transition occurs from this plotting of points on number line to making a graph, we can see that these bell-shaped curves have a lot of information in themselves. And also it can be seen that the major change which occurs is that each bell curve carries local information of the neighborhood. That is, if we take any score, let's say we take a score of 52, the curve which is relying on the peak of this point 52 has probabilities to offer of the existence of scores near to it. That is, if we look for the probability of any score, let's say 51.5, which is very close to 52, to exist, so as per this probability curve, there are very high chances that there can be a score of let's say 51.5. But then, as the curve it starts spreading, the probabilities of the scores away from it start decreasing. That is, if we consider the curve which rests on the score 52, and as per that curve we look for the probability of a score of 97, so it is way too low. But then the local information which is carried, or the local evidences which a single curve has to offer, is not sufficient. So then what can be the immediate course of action which can be employed, taking into concern the limitations? So in such a case, we need to take an aggregate of all the predictions. That is, for any given score, we have to look for the probability of the existence of that score offered by each curve, and to further take an aggregate of all those evidences and form a separate curve which is called as a smooth continuous function. And here it can be seen that the very nature of this curve is pretty smooth, but then it has also two peaks, and this is the reason why it captures the specific details and also the broader patterns of the data. But then the continuous curve is subjected to the following cases. There can be the following eventualities which we might have to face in case of the formation of this curve. The first case, as it can be seen in this picture on the left side, is that the curve is way too narrow, where even a small fluctuation, a small detail is given way too much of importance, and then this makes the curve to be way too noisy. And on the extreme right side, we have this curve which is way too wide, where even the important features, the prominent features of the curve are missed. And both of these cases are detrimental, or they can have an adverse effect on the precision with which we can make estimate about the larger population. And thus this graph which we have in between these two extreme cases is the perfect balance of these two, and thus we can see that the curve should be optimal. That is, the curve should capture the main pattern, but then it should also not get distracted by noise. That is, it should not get distracted by the small fluctuations, the fluctuations of very negligible magnitude. And thus this choice needs to be made with regards to the bell-shaped curve, which is established over the each point in terms of how wide or how tapered it should be. That is, this curve, this continuous curve, it is not independent, it is dependent upon the bell-shaped curves which we have formed over each point. So thus this choice needs to be fundamentally made with regards the bell-shaped curve in terms of how it should spread, or to which degree it should spread, because otherwise we have seen in the normal distribution that the two ends of the curve literally stretch from minus infinity to plus infinity. So here we need to make this choice, or in some other words we need to regiment this curve in terms of its spread, and this decision of making this regimentation of the spread of the curve is going to be the selection of the bandwidth. But then there are going to be many ways, there are going to be many techniques, many mathematical tools which will determine the selection of the bandwidth, and one of those many techniques is the cross validation. And this is the sheer reason why I had made this generic statement at the very beginning, that cross validation forms a medium to the bandwidth selection. That is, cross validation is one of the technique to select the bandwidth. So, as I have said, cross-validation is one of the many techniques to select the bandwidth. So what are those other remaining techniques? So we have logistic regression, which is something which we have dealt with in the last semester in the course based on the linear and the non-linear models. We have the k nearest neighbors technique, we have the support vector machine. But then, what is so special that we choose cross-validation over all those techniques? So the speciality, or the unique feature which this technique of cross-validation has to offer, is that cross-validation gives us the allowances to compare all these machine learning methods and to get a sense of how well they work in practice. That is, cross-validation is nothing but a provision to make comparisons, or to do this comparative analysis of the performance of all the methods, all the models, and then to make decision based on the performance each model has. So here the very first question which arises is, what is basically cross validation? Because we have seen that it forms a visceral part of this presentation. So this cross validation is one of the method of machine learning where we divide the data into two parts. There are two bifurcations of the data, where the first part of the data is the trained data, the data which is given certain training, which is given certain treatment, and then we have test data, or data which has which has been given no training, and then on the basis of the training which we have given to this particular lot of data points, we check as to how this particular lot works on the untrained data, to otherwise check the efficiency of that very model, because this is all machine learning is about. We train that particular mechanism to work in a certain fashion, and then it keeps working on its own. So then, now coming back to the example which we had dealt with in the beginning, let us take this example to a general sense. That is, in this example we had only 6 scores, but let's say we have k scores. We now come to the point of generalizing it. So let's say we have k scores, or we have some number of samples, and we divide it into k folds. We divide it into k number of parts, and the process here is to divide this data into these k folds and to consider one fold as the test fold and the remaining folds as the trained folds, and to see as to how the trained folds work upon the test fold. But then this question immediately arises as to how this decision can be made as to which fold would be the which fold would be the test fold, and which of those folds would be the trained folds. So then there is no need to make decision, because we would be considering combinations where each fold would be given this chance of being test fold, and then we would be considering the performances of all the combinations, and we will select the combination or the model which has the maximum efficiency or which performs the best. So here, as we can see, we have these models where we have combinations of the trained and the test data, and we can see that there is this accuracy in terms of the estimates which it has made, and we select the model which has the maximum accuracy. And in context of the example which we have dealt with in the beginning, this model selection is in terms of this sense as to which spread of the bell curve would be the best or would give the optimum continuous function. So then, as I had said in the very beginning, that this cross validation further disseminates into least square cross validation and the maximum likelihood cross validation. So then the question which arises here is that what is the point or what is the conceptual impetus on the basis of which this dissemination occurs? So this dissemination occurs on the basis of the training which we give to this so-called trained data, the sort of programming which we do to this trained data. So there are two types of trainings which we can give to the data. So the first uh, type of training which we can give forms the least square cross validation, and the other type of training which we can give forms the maximum likelihood cross validation. But then we need to see in details as to what is the exact sort of training which we give to each of these type of cross validations, and how do they differ from each other. So here we have the least square cross validation, and the purpose is of course to find the optimal bandwidth. In both of the cases the purpose is the same, but the method is different. So in the least square cross validation we leave out a single data point, it is the test data. We estimate the density using the remaining data, and we compute the squared error of all the left out at the left out point from the uh, remaining data, and we repeat it for all the points, and this minimizes the integrated squared error for the optimal bandwidth. Whereas in the other method of maximum likelihood cross validation, we compute the log likelihood of the left out point, and we repeat this process for all the points and further take the sum of all the log likelihoods, and it maximizes the likelihood for the optimal bandwidth. But then the differences which lie in between these two methods is that the least square cross validation is a more robust method which avoids the spikes and thus leads to smoother estimates, whereas the maximum likelihood cross validation, it can lead to under smoothing, which is not always reliable and thus can give necessary importance to noise. That is, it can get uh, way too disturbed, or it can get disturbed much more than necessary even by small fluctuations. But then throughout this presentation I have been using these words like estimate, like parameters, like local evidence, loss of information, etc., which have a lot of relation, or they have got a lot to do with the courses based on the inference theory, like the testing of hypothesis, like the theory of estimation. So what is the basic difference between the kernel density estimation and the conventional inference, or the conventional theory of inference, which further includes the testing of hypothesis, and the theory of estimation? So here are a few differences. Firstly, the difference lies in the very nature of estimation. In the conventional inference theory, we have parametric distributions, that is, the distributions they assume a certain form, whereas in the kernel density estimation, we do not assume any distribution, it is a non-parametric distribution. Second difference is in terms of the parameter, because in the conventional inference theory, we estimate the parameters in terms of the mean, in terms of the variance, or some other parameters, whereas here we do not have any such parameter, but here the bandwidth controls the smoothness in terms of the estimates which we have to make in terms of the larger population. In terms of the number of assumptions, the conventional theory of inference assumes a certain distribution, as I have said in the first point itself, and also the number of assumptions which are held are way too large in number, whereas in case of the kernel density estimation, we have very less assumptions, and the basic foundational ground is way too flexible. And fourth, the last and the most important difference is in terms of the purpose which we have to meet. In the conventional theory of inference, we have to test the hypothesis, whether the hypothesis which we have devised is true or is false for a given level of significance, for a given level of a given degree of freedom, and also we have to estimate the parameters. Whereas in case of the kernel density estimation, we have to explore the data and we have to visualize the density. And thus the key differences, or the sum and substance of the difference is this, that conventional theory of inference is a model driven inference, that is, the inference is in terms of a certain model, whereas the kernel density estimation is a data driven smoothing, that is, we have to make sure that the inferences or the estimates which we have to make in terms of the population are smooth. They do not get way too influenced by small fluctuations, neither do they miss the important curves or the important niches and orifices of that particular pattern. And thus the kernel density estimation, or in specific the bandwidth selection, turns out to be a part of the non-parametric estimation. And thus here I am done with all which I had to present on this topic. So it's the time for acknowledgements. So here is the list of all the resources which I have used to design this presentation and to gather the content for this presentation. So once again and for the last time, I would like to thank you for holding on with me for such a long time, because almost all of my videos have been a bit too lengthy. And also I would like to thank you for the immense support and your patient listening, for your precious time, precious attention. I wish you all the very best. May all your dearest dreams come true. Thank you. Thank you very much.